Hello, from my home to your home. In the next 15 minutes, I would like to talk about the limitations and the possible ways of improvements when constraining the Hubble constant from strong gravitational lensing. Since home is where the standard cosmology is, I would like to assume a lambda cold dark matter model for the remainder of the talk. Then, probes of H0 become probes of cosmic distances, because every cosmic distance, like the co-moving distance, can be split into a part proportional to H0 here and a part involving the expansion function of the universe. Now, the Planck collaboration has measured the cosmic distance to the cosmic microwave background. This was an all-sky observation of the early universe, and they obtained an H0 value of about 67 kilometers per second per megaparsec. In contrast to this, we can also restrict ourselves to the local universe in late cosmic times. Here we can use Cepheids and supernovae, as for instance done by the Schuss collaboration, and we can get a local late time H0 value of about 73 kilometers per second per megaparsecs. These two values should actually agree with each other, but now we have arrived at a 5 sigma discrepancy of these two values. Now, how can we understand this Hubble tension? Strong gravitational lensing is supposed to come at its rescue because it covers a wide range of intermediate redshifts. It can use various probes as sources and as lenses, and it's only based on the simple assumption that light bundles are deflected by masses along the line of sight. So, is strong gravitational lensing now an optimum probe to resolve the Hubble tension? In order to further pursue this question, we have to see how we can infer the Hubble constant from strong gravitational lensing. So here we have a light-emitting source located in the source plane at redshift ZS. And this source emits light bundles towards us as an observer. If there were no gravitational lens in between us and the source, we would see a single image of this source. Yet we have a mass density lying in the lens plane here at redshift ZL, such that the light bundles coming from the source are deflected along multiple pathways around this strong gravitational lens. And as a consequence, we do not see a single image of the source, but we see multiple highly distorted and magnified images of the source lying in certain configurations around this strong gravitational lens. In addition, because these light bundles travel along different pathways, they arrive at different times at our position. So we have as measurements arrival time differences between the different multiple images. Of course, we know the redshifts of the lens and the source, and we can also measure the distances between these images on the sky. And now we can combine all these observables into the strong gravitational lensing formalism, which gives us a formula to connect these observables and to give us an equation that contains the Hubble constant. We can see this on the right-hand side, where we have the arrival time differences, TA minus TB, and this is equal to a product of a prefactor containing the redshift of the lens, times a factor which contains cosmic distances, and a factor which contains the information of the strong gravitational lens. And here we have a differences of gravitational lensing potentials between these multiple images A and B. And again, here we see that the Hubble constant enters over this distance ratio. So the arrival time difference is inversely proportional to the Hubble constant, as in every other distance measurement. This gravitational lensing potential difference is again split into two parts. One part is the geometric deflection, which is caused by the different light paths along the line of sight. And the second part here is a difference in what we call the deflection potential, which is the time delay caused by the differing masses between these two multiple images in the lens plane. So if we now want to infer H0 from this equation, we need to have the arrival time differences, the distances between the images. We also need to know a distance redshift relation because we want to convert the measured redshifts into distances. And of course, we need the local lens properties at the positions of these images. Unfortunately, we only have this single equation. So of course, we have a lot of degeneracies that we have to break in terms of lensing and in terms of the relationship between the lens and the cosmology. Otherwise, we cannot infer H0. And this is why I first want to discuss now all the degeneracies that can occur before we can find ways to break them. The first class of degeneracies contains the degeneracies in the lens plane. Here, the formalism is degenerate in the local lens properties, meaning that each of these degeneracies that I show you are applicable to the multiple image systems individually. And they only constrain lensing properties at their multiple image positions. So let's have a look at the first degeneracy. So we assume now that the deflection angle is given as the gradient of this deflection potential. And then after some calculations, we find that all observables remain invariant if we allow for perturbations in the deflection potential at the image positions, such that the difference of these small scale perturbations can be attributed to an overall shift in the source position, which is not that hard to achieve because the source is not observable to us. This is the first degeneracy. The second degeneracy of this equation is that we use a Poisson equation, which relates the deflection potential to the deflecting mass density, or rather a scaled version of it. Now, using all the mathematical tools that we have to solve this equation under certain boundary conditions, we find that we can perturb the mass density distribution, and we can do this in a really broad way because all perturbations are allowed which just keep the deflection angle at the multiple image positions to being equal to 0. This is the most general class of invariance transforms that we can apply to the single plane lensing theory here. Now let's extend this idea to the line of sight. In the line of sight, we have another underdetermination problem equal to the one in the lens plane, because we can only measure the integrated signal along these different light paths. And this means that we can attribute different parts of the signal to come from a background metric, to come from perturbers, or to come from our strong gravitational lens. This is a freedom of a gauge choice. And because dark matter is invisible, we have this choice to redistribute the matter because we cannot trace it individually. So we end up with two different scenarios that can leave all the observables invariant. On the one hand, we can assume a ΛCDM background cosmology and then put perturbers along the line of sight in this lensing potential, which now gets a bit more complicated because it also includes line of sight perturbers or even satellites close to the lens plane. We can now make our life easier in terms of the lens by including part of the perturbers into the background metric. This is, for instance, done in the Dyer-Roeder metric. But here, we complicated our cosmological background metric. So both of these scenarios seem to be likely and seem to be feasible. It's just that it depends how we split up the integrated signal into these different parts. This is as worse as it can get in terms of degeneracies. Now, how do we use additional information complementary to the strong lensing formalism in order to break these degeneracies? The first one concerns the lens plane, and there we can assume a mass density profile, a global one, which connects all these multiple image positions. And here we find that power law profiles seem to work very well on galaxy scale and on galaxy cluster scale even. There seems to be a conspiracy for universal mass density models. Why is it combinations of power law profiles which seem to fit so well here? This is a question that can actually be answered very trivially, as I recently found out in this work. Because take a look at scale-free Newtonian gravity, which is supposed to dominant interaction between all the individual parts of such a strong gravitational lens. Scale-free gravity causes self-similar structures. So it's pretty much legitimate to assume that all the parts can form a self-gravitating ensemble of particles, and that each particle has a certain probability density function of being at a certain position. And this is motivated now to have a power law ansatz based on Newtonian gravity being the dominant interaction. The thing that we don't know here is the power law index, and because it's a probability density function, we still have to normalize it. And here comes the information of the macroscopic part, meaning of the continuous mass density that we would like to represent with these particles. Because the normalization constant here is obtained by stating that we find this particle in the structure with a probability of 1 if it belongs to the structure. And here we integrate over the entire geometry and the entire extent of our structure. And this means that the normalization constant encodes the macroscopic mass density profile in this n of alpha and all the other quantities which capture the geometry of our structure. Now we can ask, what is the most likely configuration of all of these particles? And this allows us to gain an equation which connects the macroscopic mass density function, and in particular the unknown power law index, with a realization of this particle ensemble, which gives us the power law index here over this equation. So this is a very general form connecting macroscopic and macroscopic picture, and we can now solve it for alpha depending on which particle ensembles we want to consider and which geometries of our structures we want to solve for. And we find that our most common mass density profiles, the broken power law profiles, including the Navarro-Frenk-White profile, are just special cases of this general equation. And this means we now have found a fundamental principle and a fundamental theory which motivates why these power law profiles are good mass density profiles. This is a very good step forward in order to reason why these lens models are actually good lens models to break this degeneracy in the lens plane. Now let's have a look, what can we do with it? For instance, in galaxy scale time delay cosmography, as for instance done in the TD Cosmo collaboration, they measure the time delays, they also measure the relative distances between the images, and they use such a power law lens model in order to alleviate the degeneracies in the lens plane. In addition, to further break degeneracies, they use kinematical information from velocity dispersions along the line of sight. And as I told you, to break the degeneracy between cosmology and the lens, they also have to take a look into the surroundings of such a lens to find small scale perturbers that are not in the lens plane here and are not in the lens. So in this forward modeling approach, which is based on Bayesian statistics, they insert all the observables that we have, and they now want an a posteriori probability distribution of the inferred Hubble constant from this. But unfortunately, we have further parameters and further variables, namely we have astrophysical parameters like the power law index, but we also have here the parameters of the expansion function of the universe, because we still need to sample the expansion function when we want to have these cosmic distances marked in green here. And so what's missing here is, how do we get the expansion function in the least model-dependent way and to be able to solve for H0 in the most efficient way as well? Because everything that we have here costs a lot of computing time in order to sample the entire space of all these parameters to get this a posteriori probability distribution. And here I would just like to briefly mention that my colleague and I, we found a very clever way to sample the expansion function of the universe without making any assumption about H0, not even marginalizing about all possible ways or possible values of H0, by using supernovae as additional complementary probes, and by assuming that the degree of freedom which is taken over in the model by H0 can be represented in the measurements by the absolute magnitude m of the supernovae. You can have a look at the details in the paper, but you can have a look at the evaluation graphs now. When we take a look at the relative precision with which we can reconstruct this distance ratio from the Pantheon sample of supernovae, we find that we lose about an order in precision compared to the values if we use the Planck data. So these are really very precise compared to the Pantheon data of supernovae. But if we use the Planck values, we have to impose a cosmological model. And we do not want this because we want to have at least model-dependent H0 as good as it gets. And therefore, we can sample now E of Z based on the complementary data of supernovae, and we lose precision, but we gain model independence. This is as good as it gets if we want to infer H0 from strong gravitational lensing using also complementary data by kinematics and also complementary data for the line of sight like supernovae. So let me now summarize. If we want to get H0 from time delay differences, we have the advantages here that we have well accessible observables. It's just a few time delays. We have the luminous part of the lens. And so overall, we get a very good understanding of all the relevant astrophysical effects. In addition, we also have a very simple lensing formalism, and we understand all its degeneracies now in terms of physical interpretations. This is my big contribution that I made here to understand what do all these degeneracies mean and what is the most general class of all these invariance transformations. And in addition, we now also understand why these morphologies of the lens models that we usually based on heuristical fitting functions, why they are actually good profiles also from fundamental principles. So we have an understanding of the occurring lens shapes, and we can motivate this based on fundamental physics. So far, so good, but now it's the question, is percent precision feasible given all these observables and all these degeneracies that we know? The other question is percent precision actually reasonable? Because nobody tells us that the Friedman cosmology is the unique solution compatible with all our data. And last but not least, the question that I also want to discuss with you is, can this approach really solve the Hubble tension? Is this possible? I'm looking forward to very vivid discussions about this topic. And in the meantime, I would like to thank you for your attention. And if you want to see my own idea how we can resolve the Hubble tension, have a look at this paper. Thanks a lot, and see you soon.